Very good. My name is Eric Taylor, and I will serve as your host today for this webinar. Again, today's webinar is Tracking Forest and Landscape Change from Space using the ForWarn system. Today's webinar is presented by Steve Norman and Bill Hargrove, research ecologists with the USDA Forest Service Southern Research Station. We will get started. I'll pass the mic over to Steve. Take it away.
Thank you, Eric. And thank you all for attending this webinar and for giving us the opportunity to talk about this exciting new technology. I'd like to also recognize and thank my colleagues, three of whom are shown here. Bill Hargrove of the USDA Forest Service Eastern Threat Assessment Center, who sits beside me here today, and Joe Spruce of NASA's Stennis, and I think he's online, and Bill Christie, who works with us here at the Threat Center in Asheville, North Carolina. So this presentation will cover four related topics. First, we're going to provide a brief overview of why forest monitoring has shown to be so difficult over the years. Second, how the ForWarn system was designed to meet many of those difficult challenges. Third, we'll cover some intriguing examples of how ForWarn captures disturbances in near real time. And fourth, and I would argue perhaps most significantly, how ForWarn can improve our long-term monitoring capabilities. And then that will be followed by a summary. So 6 challenges of forest monitoring that I can think of. You can think of these as Herculean labors, things we're charged to do as the agency here we work for as Forest Service people, and private land folks have many of these similar needs as well. We're asked to track all forests, the condition of all forests across all lands, across all jurisdictions. We're not just interested in what happens on our own back 40, but what happens in neighboring lands. And so that's a rather broad charge that we've been given. We're asked to track both disturbances and the results of those disturbances. Sometimes it's easier for us to see a fire when it happens, or some type of disturbance that we have other data that gives us information about. And other times the outcome is really what we're after more than just that a disturbance occurred. We're interested in understanding what's going on across seasons, not just the growing season, but in the spring and the fall when things are changing, and also in the winter. There's a lot that goes on throughout the course of the year. We want to have a monitoring system with near real-time capabilities, so we can see something when it happens as soon as possible. And that's important because it gives us the power of intervening early on when we might be able to make a difference. We want to be able to also capture gradual decline, the slower things that change, delayed disturbance impacts, not immediately, but after a few years, things may still be changing. Part of that change is positive, it's recovery, and sometimes it's very serious, like type conversions that happen because of a disturbance, say. And it would be mythological fantasy to say that we're monitoring everything we care about. The best we ever can really do is to monitor indicators that make sense to us locally or regionally. And so we need indicators that simply make a lot of sense for us. And in the past, we focused a lot on local indicators. We track local indicators of change. We compare those with our expectations or our desired conditions, and then develop some type of response. Well, we have other assets we can bring to bear. Remote sensing indicators of change certainly are also something we can take advantage of. We can compare expectations or desired conditions based on those data, all the while informed by what's going on and what we care about locally. But the value of this broader scale technology is a little bit different. It's to give us a coarser sense of what's going on, and that may inform where we have the most problems, where in the landscape we might focus our local attention to come up with some local response. And that is really the arena in which ForWarn is playing. It's a remote sensing technology that helps us understand how changes occurred with respect to our expectations to help focus our attention locally to those places where we can work more efficiently. So there's quite a few monitoring technologies that are out there. ForWarn isn't the only monitoring technology we've thought of. And they vary a lot in terms of how often they occur, how often the monitoring observation occurs, and the extent of the coverage of that monitoring. Sometimes when we have a disturbance, say like a fire, the remote sensing laboratory goes after those fires and analyzes the post-fire severity in pretty great detail. In other situations, we're continuously measuring the drought across the United States. Those can sometimes occur just when the event happens, like a fire. We just go to the fire perimeter. Sometimes we monitor everything we can. And so ForWarn, because of the satellite-based technology, is a weekly monitoring technology, and it covers all of the continental United States. The ForWarn system takes advantage of an indicator called the Normalized Difference Vegetation Index, or NDVI, and it's using satellite technology from the eMODIS and MODIS data streams. MODIS imagery is an effective 232-meter resolution, which is about 13 acres or 5 hectares. And the trade-off of that resolution that you might say is awful coarse for maybe understanding what's going on at stand level is that it happens at very, very high frequency. We have 46 periods per year, 46 separate products per year that are delivered at 8-day intervals. And the way to achieve this, given the high frequency of clouds that get in the way of seeing what we really care about under the clouds, is through a moving 24-day window that moves at 8-day time steps. MODIS satellites have been up there since 2000, and so it gives us a really rich historical database which we can exploit to understand context of the present conditions. And so the ForWarn system includes this time series and all the richness that it conveys, along with change maps that are produced in near real time since 2010, and are available on the website shown here, forwarn.forestthreats.org. So the change maps that you'll see on that website use a number of different baselines. We have a 1-year early detect that tries to capture the condition of the forest relative to the conditions at the same time of year, a year earlier, and a standard, a cleaner 1-year product, and a 3-year maximum baseline, a product which looks at conditions relative to the maximum you've ever seen, which gives you a sense of how things are compared to the potential vegetation that's been at that site. The all-year average, which is awful important when you're trying to sort out climate artifacts that might be in there, like drought or unusually early or late falls. And then an all-year tightening based on a more sophisticated way of looking at landscapes. So the NDVI, as I mentioned, is a primary indicator that the ForWarn system's using. And I'm not going to dwell on this much, but it simply looks at differences in plant reflectance between a portion of the photosynthetically sensitive part of the spectrum and the near-infrared, which plants simply don't really want to absorb so much because of all sorts of reasons, and so it's reflected more. And this ratio allows us to get a robust sense of how quote-unquote green the observed vegetation is at a given time. And so then week-to-week or year-to-year comparisons of that let us infer stress or seasonal change in what you can think of as greenness. Now, given this powerful indicator, we gain insights into what we call land surface phenology. It's how this greenness changes throughout the course of the year. And that land surface phenology gives us insight into vegetation type. Here we have 9 examples of deciduous forest across United States. And you can see over these 12 years or so a great deal of variation from winter. I'm going to try and use this. A great deal of variation from winter to summer, winter to summer, in all these, and that's characteristic of deciduous forests. They lose their leaves every year. In contrast, when we look at something like evergreen conifer forest, winter to winter to summer has a lot less amplitude, a lot less variability, and that's simply because they keep their leaves on. They're evergreen after all. Grass, on the other hand, looks completely different again. It has a lot of variability quite often, especially when the grassland's more productive. So winter to summer, winter to growing season, you see a lot of peakedness, but it's also a lot narrower than what we saw with the deciduous forest, and that's because of the flashy phenology of grass-dominated vegetation. What you'll also notice is year to year there's a lot of variability, and that's usually related to climate variability. Drought years make more productive years. Grass responds very quickly to that. So we can use our insight of vegetation type and how it responds to learn a lot at a resolution which is pretty informative for a lot of questions. So the general profile we're talking about land surface phenology looks like this: winter, spring, summer, fall. Low NDVI in the winter, spring greens up quickly, you end up with a summer peak, fall and winter drops down. Now, when we talk about change in greenness with respect to what we expect it to be from some normal phenology profile, if spring's unusually early, it's going to be, according to this color gradient, it's going to have more greenness, and so we're going to display it as blue. It's bluer than normal, meaning it's greener than normal. But if it's a late spring, it's going to be falling over here, so it's going to be departed. And the later the spring, the more departed it would be as it grows up. Now, if it was a drought year, instead of being a typical summer, the line might be down here, right? And then in the fall, if it's an early fall, it will be less green or more orange, more red than normal. If it's a late fall, it's going to have greenness later than it normally does, and so it will show up as bluer than normal according to this color scheme that ForWarn uses. So this also is powerful, not just about that sort of climate variability that's out there, but also to pick up disturbances. Sometimes we see a big dip in the late winter, which is related to heavy snowpack. The snow accumulates over evergreen foliage, evergreen vegetation, and it masks the greenness that's there temporarily, as long as that snowpack is really heavy. During the growing season, this technology allows us to see things like defoliating insects, or wind, or hail, or a hard freeze, or even mechanical activity like thinning if you remove some trees, or a light surface fire. It can also pick up stronger disturbances that are much more severe during the growing season, any time of year even. Severe blowdown, severe fire, a patch clear cut, or something like urban development. And that departure can continue through the growing season, or as we saw here in the spring, it can recover pretty quickly. And the thing to keep in mind again is the farther down you go, the less NDVI relative to that normal baseline, the more yellow, orange to red your map is going to be. So these maps, they come at us and we see all sorts of patterns. We just don't see the normal blue. A year like 2011, say, we see all sorts of variability here in the forest vegetation that's shown. And so when you're trying to make sense of these, you need to take advantage of tools. You need a toolkit of tools that you use, cues that let you hone in on what it is you're looking at. And one of those is extent. The more extensive a disturbance is, the more likely it is to be a climate-related phenomenon rather than some localized disturbance. And here in this map of Texas in 2011, which was a drought year, a lot of that variability, you see that reduction in greenness, departure from the blue, results from the drought. However, right here, inside the circle, you can see there's that dark little patch. It's enlarged here. This is the Bastrop fire, and so you can see the background from the drought where it's pretty red, and then the area that burned that's really, really dark red. So the shape of the fire shows up very nicely, as does the intensity of it. A year later over here, you can see the relative change in intensity, and the edge really come out very clearly as well. So extent, the shape of it, the intensity are three tools in the analyst's toolkit. Something that you can do, because these are dynamic maps, is look at behavior. The condition of greenness is not just a single map, but it's a series of maps, and so you can look at how quickly it happens, how rapid the onset, how long it lasts, by looking at NDVI time series. And I'm calling that here behavior, because it's the behavior of the anomaly or disturbance that you're looking at. That's an important clue. Another great thing is agreement. That means agreement with other data. The ForWarn website is an assessment website, and it brings in all sorts of these ancillary data sets to help you explore what something might be. Things like drought monitoring products, fire perimeters, insect and disease polygons from prior years. All those give you some insight as to what you're looking at when you see an anomaly. And so now that we've covered that, it's time to have a test. In fact, that's what we're going to do from here on out. And we're going to explore some cool examples from the last few years. And they're going to first focus on near real-time change observations. And so this is what we saw with a one-year change product. In other words, conditions as of June 1st, 2011 compared to the conditions 1 year earlier at that same time of year. So I'm not going to put them on the screen, but there are anomalies here. There's things that, everything's not blue. So what might it be? And this is where we're going to do the polling over there under your name on the left. Is this A, drought, B, tornadoes, C, deforestation for airport runways? Again, drought, A, drought, B, tornadoes, or C, deforestation for airport runways. Seems like most people, there's at least one person that thinks it's deforestation for airport runways. So Eric, if you could pop that up. So some people think none, meaning I guess non-responding. So most people got it right. These are, I'll move to the next slide. These are tornado tracks from this absolutely shocking tornado outbreak that happened early in 2011. And these arrows, the white areas here, are showing you where there are discernible scars, and they're huge in extent, right? 50 miles. That's how we know they're not deforestation for airport runways. You know, if they were going to build an airport, it would actually look like this, but not at this extent, right? We know it's not drought because it doesn't affect all the vegetation, just these streaks, and so the shape, the edge tell us tornadoes, right? When we zoom into places like Tuscaloosa, we can look at this NAPE imagery. This is the sort of stuff that Homeland Security wants. If they're going to bring in disaster assistance, they want to understand this sort of detail, and that's not really what ForWarn is trying to do here, but we can use that to get some great insights about what ForWarn has given us. This is what ForWarn looks like over that urban tornado. And with the benefits of time, especially looking at this time series, we can see how it manifests itself in the NDVI profile over time. Up here in the blue, areas that were not affected, you can see it's a normal year in 2011, just like it was in 2010 or 2012. There's no discernible impact at all. You move here to the core of it, the main part of the track in red, you can see that the tornado hit and it had a big impact right away. You move here to the yellow and we get a sense of relative severity. The impact is occurring at the same time of year, but it hadn't depressed as much. And of course, We'll get into this more momentarily, but you can see in subsequent years this start of the recovery process. So here we have another example from northeastern Tennessee, about the same time. And there's a little DEM shadow going on there, so you can see it's on a south-facing slope mostly, on a ridgeline. We'll do another polling here. Do you think this is strip mining, hail, or a tornado? 2 different dates, a month apart. And you can see the change with respect to what is normal for that time of year. Strip mining, hail, or tornado? A lot of people, the majority consensus of assessors here seems to be on B, hail. Now there is mountaintop removing, there's a lot of strip mining that takes place here, but it kind of came out of nowhere suddenly over a big area, and as you can see by July it's declined quite a bit. It's not there so much, right? So it can't be that. It's long and linear, kind of like a tornado. It certainly could be, except for one clue. Its behavior is a little different than what you'd expect from a tornado, right? It's recovered, half recovered by July 3rd, right? Which leaves us, in retrospect, you can see how it recovered here in the orange. In this particular pixel, turned out to be a normal growing season after that. Its ephemeral behavior tells us that it's likely to be something like wind or spring hail that the vegetation was able to overcome from. It's not a more severe disturbance, such as what you'd expect with a legitimate tornado. So here's another really cool thing we did, and although ForWarn's change maps only go back to 2010, this is a known event that's kind of interesting, so we made a special product which you can view and explore on the viewer from April 30th. So sometime in April or so we had something happen here apparently. Missouri's all red, Tennessee's kind of red, Arkansas has got something going on too. Is this heavy snowpack? Is this drought? Or is this hard frost? A, heavy snowpack, B, drought, or C, hard frost? And we have a little bit of an array. Most people seem to be putting their bets on C, quite a few on 5. This is a very broad extent. So it's not crazy to think that it could be drought. Drought quite often manifests itself very much like this. However, it is in April when vegetation is greening up. It's not quite as responsive to drought. It's really too late for heavy snowpack, and you'd expect a little more snow up north, I think, not just in a localized area like this. And so the correct answer is actually a hard frost. This is the big freeze of April 5th through 9th of 2007. A freeze of legendary proportions. You can see the temperature anomaly in the upper right up here. It affected Missouri completely and a lot of these other areas. And with this change masked here, you can see that the Mark Twain National Forest, southeastern Missouri, was hit especially hard by this event. This is Mount Mitchell here, not too far from where I live in Asheville, North Carolina, the highest peak east of the Mississippi. Up here, down here, we have the Asheville Reservoir. So this is the Blue Ridge Parkway. And when we zoom in, we can see that the higher elevations here were not particularly hard hit by this frost. But mid and lower elevations show a lot of change anomaly. Well, why is that? Well, when you compare two elevations, one about 5,000, one about 2.5, we can see why. We get a little clue as to why that pattern exists. The higher elevation here, shown with a dashed blue line, has a much shorter growing season, and when the frost hit, which is right there where that arrow is, this area was still, really before it, normally greens up too much. It was just the understory that mostly had been advancing. Meanwhile, at lower elevations, they'd made pretty good headway, and so it comes to reason that that was part of it as well. Another factor, obviously, could have been colder drainage. It's kind of hard to separate those two completely. So when we look at places like here, land of the lakes, we can even see a lake effect from this big freeze. The areas closest to these reservoirs are blue. In other words, they haven't changed much compared to, in fact, they're actually a little bluer than normal. They're still ahead because it was an early spring that year. And the farther you get, the forest here in between the lakes has declined quite a bit. So here we have another example. It's a little more complex. I'm showing the power of two different baselines here. We have a one-year baseline on the left and an all-year maximum baseline on the right. So it's on the right, it's the green, it's conditions in, where are we, 9/29/2011 compared to the greenest we ever saw in the fall of 2011. So what might this be? Might it be, well, here we have a little red, here we have some red, here we got some red, and all this little yellow scattered around. Might this be wildfires, drought, or logging? A, B, or C? A, wildfires, B, drought, or C, logging in the poll? And we have an interesting split here. I think the question's getting harder. Wait, it keeps going back and forth. So most people are thinking B and C, but there's a nice distribution, isn't there? So it's a little bit of a trick question. If we look at how it progresses, by October 7th, we see that little red dot here has turned into what I can only see as a flying chicken. That's the Pagami Creek fire that burned in the Boundary Waters Canoe area, the Superior National Forest. It's spreading from here in this direction, and there's a little lake there, and so it burned on both sides of the lake. Lake got through, spread over here really rapidly. You can see from the daily progression map how much that fire burned in a single period, in a single couple-day period. Compared to the prior year, the surrounding landscape was relatively normal. That's why it's blue. But if we look at the all-year maximum with respect to that, it's got a lot more yellow, which means conditions are a little bit different in the fall than what they've been. In other words, there was a later fall, a much later fall on some prior year in the era since MODIS began in 2000. That really comes out when you look at the next period. You can see compared to the prior year, compared to 2010, it's still mostly blue, but yeah, there was one year in that record when it was green very, very late in the year. Fire shows up. Now, interesting comparison here. You see this fire up here shows up. It doesn't over here. That's because this fire on the all-year baseline took place, I think it's about 2007. So obviously that's not going to be indicated in the prior year product because that is this has changed 2011 versus 2010. So you get different insights, you get different contexts by going to different baselines back in time. So here's another interesting example from the Atchafalaya Basin in Louisiana. And this is a series of 6 dates, April 22nd, 8 days, 8 days, 8 days through June 1st of 2010. And the white area here is development, it's agricultural, so that's just showing the forest. And this is the wetland forest of the bottomlands of Louisiana. Might this be A, logging, B, insects, or D, wildfire, based on how it changes over these 6 weeks? A, logging, B, insects, or C, wildfire. And just about everybody's on board here calling this insects. And indeed, that's what it is. We see these spring eruptions almost every year in this area. Sometimes they're extraordinary. These 5 maps here give us 5 different perspectives from about the same time of year. May 16th of 2010 in the upper left, this is with a 3-year baseline here, shows these huge areas. They almost have a measles map, right? There's epicenters where there's the greatest change, and then at the edges, the periphery, it's not as intense. And 2011, it came back, not necessarily in the same places. You move over here to 2012, that was an early spring, and so it's a little bit harder to diagnose where exactly these might be. There's a lot going on that year. In 2013, you can see a pattern that's in its intensity kind of reminds us of 2010 in some ways, but the distribution of it isn't entirely the same. And then in 2014, just this year again, we've got its own pattern. So as we accumulate all this insight, it allows us to gain some insight on what's normal, what's a normal disturbance regime for these type of forests. The defoliators here of these bottomland forests are native, and so understanding the insect disturbance regimes, it's analogous to understanding fire regimes, and that's a long-term insight that's really valuable for monitoring. Here's another example of the value of long-term monitoring and how all this can be brought together from Southern California. You see a lot of red here in September of 2011 on the all-year maximum baseline. So this is the conditions relative to the greenest that we've seen over the period of record. Is this the result of urban development, wildfires, or drought stress? And there's a little drought stress inset map to help guide you a little bit. Is this the result of urban development, wildfires, or drought stress? And most people are focusing on wildfires. All you have to do is say California. And there's a good chance that when you see a disturbance, it's from wildfire. If we look at conditions a year later, in 2012, we can see, first of all, up here, there's more drought stress. It's still not that strong, but nevertheless, it's come into play. And the surrounding vegetation outside of these core red areas that have been persistent starts to turn a little bit yellow. It's slightly departed. We look a little bit more, well, here we are in that same year, and these are the fire polygons that I've masked out. So you can see the areas that are not possibly related to wildfire by that filtering. We look at 2013. Drought's gotten a lot more severe, and oh yeah, those fires are even kind of hard to discern from the surrounding landscapes in some places because the drought's gotten producing the same or a similar reduction in NDVI as what we see in some of these forest areas. Here we have from the Saka fire in 2007, just a random pixel. You can see that it's not the highest NDVI. It's not if it's a forest, it's not a very productive forest. Maybe it's a little more chaparral here, but it's gotten a really quick drop. That's a change in behavior typical of fires, and in the years since it's headed toward recovery, but it's not linear. It's not back already by any sense to where it was. It's kind of plateaued, and now the rates declined a little bit. So here in 2014, very recently, you can see where it is during this epic drought that they're not now having. The surrounding vegetation is still a little bit off, but those fire areas still show up as significantly more departed than what they were when the MODIS period began in 2000. So here's the last example I'd like to present, and it's from Great Smoky Mountain National Park, not too far west of where I sit here in Asheville, for December of 2011. What do you think this is? Is this urban development? Is this insects? Or is this hurricane-induced landslides? And you'll see I've made the image a little bit transparent so you can see. And I'll give you another clue here too. If you click on a pixel here in Hurricane Creek, perhaps that's a clue, you can see this change in greenness over time, this NDVI profile of a decline in winter NDVI since about 2003 or 4, bottoming out about 2008. And most people are focusing on bee insects, and indeed that is correct. If you go there and you look at it on the aerial photo, you see something which is absolutely shocking. All these dead trees. These are dead conifer trees, evergreen trees. These are dead hemlocks. Gradual mortality from non-native hemlock woolly adelgids being captured by ForWarn here, and it's characteristically indicated by a drop in the evergreen portion of the annual phenological signature during the middle part of this decade. Now, interestingly, you can see a little bit of a drop in the maximum in the summer conditions too, but it's not nearly so much. This is really a winter signal that we're able to isolate by focusing just on that portion of the seasonal phenology. And we've taken advantage of that to create a map of evergreen decline over time for the entire country. And here in Great Smoky Mountains National Park, you can see a lot of these smudgy olive green areas. Those are areas where we have substantial decline. These areas in black here, because they're not under that mask, are also in decline, evergreen decline. Here in this portion of the Pisgah National Forest, we have a blotch. Here we've got a blotch and a blotch. Those are from fires. These areas here and this area, that's where we started the conversation. Down here in the Nantahala and the Joyce-Kilmer wilderness area, we've got substantial decline that has the same pattern that we saw in the previous slide of progressive decline. And so through this, what we've mapped are areas of, in part, hemlock woolly velvet-induced mortality. So in summary, satellite-based monitoring can play an important part in forest management by documenting disturbances and contextualizing change. And ForWarn, as I've shown here with this presentation today, shows how the satellite technology can be used for detecting disturbances and tracking them in near real time. And very importantly, something that's often neglected, not just knowing where the disturbances are, but knowing what happens afterwards is a especially exciting aspect of this technology. Long-term landscape monitoring of these slow disturbances and how they recover and how they might change over years to decades is important and possible with this technology. So for more information, you all can check out the ForWarn website, and we have a viewer there. You can zoom in and explore areas that you know best. And when you see something that you need some explanation for, or you want to just draw our attention to it, by all means, contact us at this address. And what I'd like to do now is turn over the remainder of the session here to my colleague, Bill Hargrove.
Hello, everyone. Can you hear me all right?
Can you hear me all right?
I hope we went pretty easily on you. If anyone's got a question, I'd be happy to take it in the chat window. Okay, here's a question. Any post-processing done with the NDVI data before presentation in ForWarn? How are cloudy days handled? Oh, yes, indeed. As you know, snow and clouds are the bane of remote sensors everywhere. But Joe Spruce and our colleagues at NASA Stennis are really up on this. And so, yes, they do quite a bit of processing to remove noise in the NDVI data track. They've got a couple of specialized tools that do this. And by the way, although our NASA Stennis colleagues are technically subcontractors, we really consider them to, for all intents and purposes, be intellectual co-owners and co-developers of our ForWarn system. And they are our production facility. They're the assembly line. And I think ForWarn is just another great example of what can happen, the kinds of positive things that can happen when you get techies, technical folks, to really sit down and talk cleanly and carefully with practitioners. And ForWarn is just an example of something like that. But yes, we process out clouds. You know, the unfortunate thing is that clouds serve to drop the NDVI, to decrease the satellite greenness, in just the same way that disturbances drop the NDVI greenness. So we have to be very careful in order to determine whether this is a true disturbance detection or whether we've got cloud contamination. Okay, here we got another one. Says, can ForWarn be used to show conversion of forest to non-forest over time? Absolutely, yes indeed. So in fact, the conversion of forest to non-forest is a big change. It's something we can see quite clearly. It's so certain things, wildfires and whole area harvests, clear cuts, are easy. In fact, we can see much more subtle differences than that. So for example, the example that Steve Norman showed of the Atchophilia insects, these are much more limited reductions. So yeah, clear cuts at least at the MODIS scale. Now you remember, MODIS pixels are about 13 acres in extent, and so that doesn't mean the entire MODIS pixel has to change. It just means that some part of it has to change enough so that we can see a difference. Okay, boy, we're piling them on now. One challenge our industry faces is estimating where insecticides or herbicides may be used in forest management. Simply using USDA land cover data overstates potential use. Is there a way ForWarn may be helpful in quantifying where pesticides might be used? Well, that's an interesting question. I'm not sure I'm smart enough to address that exactly. But let me point out instead that we've got a product that we're very proud of that's available in our viewer. We call it Pest Proximity. And so the idea is you get a new ForWarn image, and there's a disturbance, and you're pretty sure it's caused by an insect or a disease. You can simply click on the viewer, and the pest proximity layer will return in an area prioritized list all of the insects and diseases that have been detected by the aerial survey folks inside the Forest Service over the history of aerial surveys. And so we think of this as a way to generate essentially a most wanted list or the usual suspects list. So you can quickly get an idea about the likely candidates among insects and diseases that might be in action. So that might be something that you could think about that might help with regard to the selection of a pesticide. I'm not sure I really answered that question, but I'm going to push on. Here's one. How does someone like me that might be doing an extension activity get access to data or specific maps for a specific area of interest? Well, there's two things that come to my mind. One thing that's the smartest thing we ever did is something we call a Share This Map URL. So you can be looking in the viewer, the Forest Change Assessment viewer, that the website is on the screen here, and you get a particular extent and a particular set of maps selected, and there's a little thing that says Share This Map, and it puts together a URL, and you can cut that out and paste it into an email and send it to anyone. You put it in a document, put it on a web page, but the most common thing is to send it in an email, and anyone else can click on that URL, and the viewer will open looking at exactly the same extent and exactly the same maps that you had selected. So this Share This Map URL is really a great way to foster communication and collaboration. But let me say one other thing, and that is if you want to actually get your hands on the data, the ForWarn data, we have two web map services. There's a WMS service and a WCS service, and I'll skip the technical jargon, but this is just a way that you can quickly download into your own local GIS some of the same kinds of things that you see in the viewer. So in this case, if you wanted to prepare printouts or something to share with a particular forest, or if you wanted to actually do further analysis inside your own GIS yourself, this WMS and WCS web services are the easiest way to do that. Okay, how do you account for clear cuts being called non-forest? Okay, I'm not sure I entirely understand the intent of that, but notice that we are using a mask in this FCAV viewer, so we're only showing you forest, but that mask is a very liberal definition of forest, down to perhaps only something like 30% cover. Now I should mention at this point that we've got a new viewer that's under development, and the FCAV2 will show all lands. So this filtering at the very end to only show forests is the very last step. ForWarn has been detecting vegetation disturbances in all vegetation of all lands, forests, crops, rangeland. And the second viewer that's under development, about to be released, has a masking capability. So it shows not just forests, but all lands. And then the user has the ability to turn on and off selectively particular masks for particular vegetation types. So I hope that helps with that one. Okay, let's see. Yes, someone's saying, yeah, we need a webinar for looking at the viewer. And we will do that probably at the beginning of the next field season. And like I said, I hope we'll have our new FCAV2 viewer by then. The other cool thing about the FCAV2 is that it works on portable devices. So smartphones, tablets, you can actually carry this thing out into the field and look at the ForWarn maps as you're in the field. Okay. Here's looks like a final question. Are data in ForWarn available for areas outside the USA? Well, we get this one a lot. We are in the USDA Forest Service, and so we are currently only doing the conterminous United States. But of course, these same technologies would be, and in fact, would be extensible to North America. In fact, we've also done some preliminary work on the state of Alaska. So, and Alaska, of course, has a lot of forests, not very many other ways to examine it. And of course, there's lots of fire in Alaska, lots of insects and other disturbances. So remember, we've got to sort of crawl before we can walk and walk before we can run. Okay, I think I skipped one. Future of ForWarn with the next generation of polar orbiting satellites. Yes. So we've got two MODIS sensors at the moment on Aqua and Terra. The notion that we might lose one or the other of those keeps me up at night. But we are starting to investigate the next generation of satellites, which are, of course, a little bit different. And in particular, we're trying to develop new ways to kind of bridge across between having one foot on one remaining MODIS sensor and another foot on the VIIRS sensor. So starting to think about that, but we are knocking on wood and hoping that our MODIS sensors continue for a long time. Okay, let's see. Is the NDVI data post-processing effort done solely for you guys, or are they made before the data are released for anyone? Okay, I'm not sure I entirely get that, but everything we do is custom. So these NDVI polishing efforts that I alluded to earlier are done in-house by our team at NASA Stennis. And I should mention also that all the products all the ForWarn products none of them are standard MODIS products. These are all customized, specifically designed for forest uses to maximize their utility. Okay, let's see. Papers describing the disturbance detection methods. Yes, if you Google my name, you'll find at least a couple of papers out there on our disturbance detection techniques. And yes, they're on this forwarn.forestthreats.org is a very deep and wide website that will tell you everything you want to know about the ForWarn system. Okay, clear-cut data often look like developed land. How do you know if it's forest or non-forest? Yeah, again, our strategy is not to really separate or keep careful track of vegetation types, but instead, especially with the new viewer, to track disturbances across all lands. And so to some degree, we're sort of pushing that onus out onto the local users who we think will have the local expertise and the local knowledge. All right. Any other questions?
While we're getting some more questions, let me pause there to go ahead and push out the satisfaction survey. And recall that if you do want CEUs, you need to complete the satisfaction survey as well as the quiz that follows. What I'm going to do is I'm going to push this out to you, so it's going to pop up into a new web browser window. That web browser window may actually be in front of your webinar window. So just be aware that you might need to move some windows around. If for any reason this does not open immediately, and sometimes it gets bogged down when we have a lot of people online, just be patient with it. It will pop up in a little bit. And if you can't get that to pop up at all while you're here online, I'm going to push that link out into the chat box as well. So you can copy that link that is put in the chat box, and you can paste that into your web browser window sometime later, anytime later, because that record is always there. And you can go through your satisfaction survey in your CEU request form. Okay? So, Bill, I'll hand it back over to you. There's a couple more questions coming in.
Okay, Bill Hargrove's back on. Let's see. Plans to release a batch query tool for many lat-long pairs or averages defined by custom polygons. Yes, of course, we've thought about these things. You know, the tendency is always to sort of recreate or build a GIS system on the web, and it's been hard for us to know where to draw the line there, but probably at least for the foreseeable future, if you've got a lot of positions you want to look at, you should contact us, or if you've got custom areas of interest, you should talk to us. And also, Bill Christie's reminding me here, he's our GIS expert, that we've got help videos and product descriptions, and also the connection information for those WMS and WCS servers on that website. And I'll give it back over to Eric. Someone is asking about whether this will be archived for future use. I believe the answer is yes. I'll hand it back over to Eric to clarify.
You bet. This webinar, as with all of our webinars, are recorded and are always available 24/7 on the forestrywebinars.net website. And not only can you view it at a later date, but you can earn CEUs through the recording as well. If you have any problems, if everybody will please be patient when trying to get the satisfaction survey. Again, you can do this at a later time. But if you have any problems with that, please just send me an email, and I'll make sure that we help you as soon as possible. I'm going to paste my email there in the chat box. It's etaylor@tfs.tamu.edu.
Well, thanks very much for the chance to talk to you, and any questions that I successfully did not answer, feel free to email us. Thanks a lot.
And this is Steve. Thank you.
All right, very good. Thanks a bunch, guys. And just to show our appreciation, everybody would have moved to the little icon that looks like a smiley face underneath your name in the participants window. And you can move that down to the applause. Don't use the raise hand, but use the applause. Let's give our speakers a big round of applause. Thanks, guys. And that concludes our webinar for the day. And if you have any difficulties, if you've been patient, if you have any difficulties getting your CEUs or fulfilling through the satisfaction survey, just send me an email.